Hello, everyone. I'm amazed how many people want to know about little ponies at this time of the day. The last slot of the session, incredible. Thank you. I was expecting maybe 5, some of the friends, but cool. Thank you so much. Do you have a good time at the NDC London? Yeah? Anybody want some awesome prizes? No? Yeah, I had a raffle ticket. I forgot about it completely. But anyway, so deep learning in the world of little ponies. How many of you there are quite a few talks on deep learning this conference. How many of you attended any of them? Oh, quite a few. So there might be, to be honest, unfortunately, I was ill, so I couldn't attend anything over the last 2 days. So there might be some, similarities maybe, but I hope you learned something new today as well. So thank you for being here. So my name is Galiya Warrier. I work at Microsoft here in the UK. I'm originally from Russia. I'm a cloud solution architect specializing in advanced analytics and machine learning. I have a little daughter, Maya, who is 4 years old. And I'm sure many parents here, you will know the challenge when you have a child who is obsessed about one cartoon and wants to have meaningful conversations with you, and you cannot really connect because that particular cartoon might have like 30+ characters, and I really cannot remember any of them. I might remember 1 or 2. I was toying with the idea, okay, maybe I can kind of spend a bit of time, growth mindset, all that, remember, and kind of do something about it. But actually, because I do, at Microsoft, I do a lot of machine learning work with customers, I thought, okay, maybe I could apply some of my skills for that. And I don't know if any of you have seen this Twitter message from one of our Microsoft guys. Obviously, if it's written in PowerPoint, it's AI. This is what we're talking about. But I'm going to show you some Python code and actually how you build some of those classifiers and how you start with deep learning. Anytime you start on anything to do with machine learning, the first question is, do we actually have data? And for real-world scenarios, you need to have a lot of data when you start approaching deep learning image classifications. We talk about 1,000, 10,000, 100,000 of samples because you want to learn as much as you can from those. And if we talk about real scenarios of, image classification for power stations, for instance, you want to understand some of the corrosion or some of the kind of cracks, et cetera, you need to know what's the differences. So it's a really, it's a massive data set you need to know, you need to have before you even start there. Obviously, for my toy data set, for my toy problem, I went on exploring the usual suspects, images, search images. Somebody has written a wonderful Python script to actually use that. So if you have any, after this talk, if you decide to go and get some of the data, use that, it's an amazing little library which you can use. And obviously, specifically for My Little Pony, there's a fandom website. Knock yourself out, any characters, any cartoons, etc. So, OK, we're good here. Everything is fine. So now now we have data. Let's talk about what this data is and how we can actually start using it in a concept of machine learning and deep learning specifically. So if you think about the image, so what is an image generally? I mean, obviously, we perceive it as a multicolored, that one of the ponies there. But essentially, from a computer point of view, it's an image which has 3 color channels. If it's colorful like this, or if it's a grayscale, it would be only 1 channel. And you have each of the pixels in that image will have some certain value associated with it between 0 and 255 in red, green, and blue spectrum. And so the kind of luminosity and all that will be associated with this channel. And obviously, it's important that it has width and height because we will be using this information later on when we build our networks. If we talk a little bit more about the basics and kind of fundamental things on the machine learning and deep learning, if I ask you, we have stepping out from little ponies, we have a problem that we have a clock, we have lots of images of clocks' faces, and we're trying to understand what time it is actually represents. And if we throw into all the coolest hype tech, deep learning into that, we might be we need a lot of samples, and we need to know how we're building it. But actually, if we think about it from a kind of domain expert perspective, we are all experts here, we'll think about it. Actually, if we look at this pixel image, and all we need to know about that, say, if you want to find out the time of the hour clock, where it is, we kind of just need to track the tip of that clock, of the hour hand. And similarly with the minute, we only need to kind of make sure we understand at which point that particular tip of the hand is. And then if we think a little bit more about this, we can say, well, it's actually, if we represent it not in a normal geometrical space, but actually we will use angles, and then we can understand that 90 degrees for an hour clock is actually 3 hours. So for the minute, it will be, again, there would be different angles will represent a particular time in hour and minutes. So essentially, we might actually derive those features where we might actually don't need to do any machine learning. We can just write a few lines of Python script or any other script and actually solve this hard problem of understanding what's in the image. So this is where you will, if you think of any machine learning problem generally, you need to have a good domain knowledge of what exactly you're solving and what are the important features in that domain which might be contributing to an output, to the final result. And this is where there are differences between classical machine learning or traditional machine learning, and this is, some of you may heard or may use already, linear regression, classification, etc. And this is where you have, on the top part, you have an input. In our case, it might be an image. Let's say we're trying to classify if an image is a car or not. And we will have some features extracted from the image in advance, which we understand if it's, it has the mirrors on the side, it has 4 wheels, some other things which might be important to contribute. And then we will use some of those traditional classification algorithms to derive an output, yes or no, in this particular case, so binary classification. Where deep learning comes in, and there are reasons why it's more popular right now, and it's due to availability of data. There are some breakthroughs in the algorithms in how these systems actually learn. What happens is, while we feed the data in, it actually starts extracting those features. So the learning there is essentially understanding what is important in the input, in hundreds and thousands of input images, to actually derive, is it a specific class or not. And this is where deep learning networks, they learn about representations. So if you look at this image, which is similar gloomy day, I think last year, Tower Bridge. So you can look at this, and if you live in London or if you don't, you kind of you'll recognize it's a landmark in the city, there is a river and these kind of things. And we kind of understand it quite automatically for us. We build those features. How the learning systems, deep learning systems will work, so they will actually, while they learning from similar images, they will learn that, well, there's a tower, there's a smaller element, so there are some edges, there are some kind of curves, and then further down in the networks, they will learn that there are towers, there are maybe that pedestrian bridge, or what's it called, whatever the word for it, so where you can walk, and then you have those cables as well on the side. So you start building that representations, and they learn from low-level features down to more higher-level features, and some of them in the middle, where you can understand what is actually the class is. And if you think of a kind of simple, again, examples where you're classifying is an image of an animal, is it a cat or a dog? Again, there are low-level features, what represents a cat, and there are high-level features going further down. So this is what essentially the networks, deep learning networks, learn throughout the process. So if we talk about neural networks, obviously the smallest element there is a neuron. And forgive my scribbles here, but essentially you have each neuron, and we will see later on in the examples that you will have millions of them. You can have millions of them in your networks. Will have a few elements. So you will have obviously the X on the left-hand side, it's your inputs. And then each of the inputs will be multiplied by a weight, W's. And then you will also have some specific bias for each of the neurons. There would be a value of a bias, which then altogether will be summed. And then there is a specific activation function which will further on decide whether this value, the calculated value, should be propagated further on or not. And there are different ways how you can do that. Any of you attended a talk by Kendall Miller about the CPUs and GPUs, etc.? No? Some of you at the back. Yeah, so essentially we do a lot of these dumb calculations at the back of it on the CPUs. GPUs are much better for that because they do a lot of calculations like this in parallel. Because we talk about millions of calculations like this happening back and forth, actually. So we will have to have a lot of computational power available to us. And that's, again, another reason why deep learning, so kind of all the concepts I spoke about and I will be talking about is being there in the academia, in the industry for a while, but we just didn't have power to use it. So this is a neuron at the higher level. And then when we talk about networks, neural networks, so we have obviously layers in those networks. And there are two, oh, that doesn't work. So we can have a very simple shallow neural network, and this has something that's been available for decades already. So you have a number of, so on your left-hand side, you would have your inputs coming in, and that could be mathematical values. It could be our images, which we then translate into numbers. There might be one hidden layer, which does a lot of those calculations, as I mentioned there on the top. And then you'll have an output layer, which will decide, let's say, the example of binary classification, is it a yes, no answer? Or if it's a multiple, there might be multiple units there. So deep neural networks, essentially what the step forward there in the last few years was that we can actually have many of those hidden layers. And that could be 3, it could be 5, it could be hundreds of those. So some of the state-of-the-art network architectures, so they have more than 100 and 200 layers there. And you'd imagine, so again, each of those elements will have a neuron and all of the summation and the activation function related to that. So a lot of calculation happens there. So this is on the layers. So anyone talking about deep neural network is just we have many hidden layers underneath. That's pretty much all is there. Activation functions is a very important concept for the deep learning. Essentially, because we do a lot of calculation, then we'll touch on the backpropagation, where we actually need to take derivatives and do the chain commands, chain functions. We need to make sure those functions are continuous and infinite in domain. And they don't change direction, they're monotonous, so they actually mathematically we can do very quick calculations on them. That's very important. And different layers may have different activation functions. And again, you'll see it in the code later, but you will have in the hidden layers, in those between input and output, you will have either sigmoid, tangents, or rectified linear unit is quite a popular one. Essentially, we will take, if you take a ReLU, if it's called, so you'll take anything, if the value is below 0, we ignore it. If the value is above 0, then we use it, use the ReLU function. For output layers, the activation functions are different because sometimes you actually doing a regression, you're solving a regression problem, so you actually want to understand the output should be the number. So you might want actually not to put any activation function. At the last layer, you want to say, OK, give me the raw values. That's all I care about. So there would be none. Sometimes you might have probabilities. You want to understand, is it a car or not? Yes or no? Is it one of these classes of ponies? Yes or no? And which of the class it is? So then you start getting into either it's unrelated probability, you have a sigmoid function, or it's which of one probabilities it is, and then there's a softmax function. So again, we'll see some of these examples later on, but this is kind of a very important concept for the deep learning. And then another important concept about deep learning is backpropagation, and this is what actually drove the deep learning popularity and hype right now, because this is how the system is essentially learned. So we start calculations, when we feed the data in, where there's x-axis on the left-hand side, we do the calculations according to our activation functions, according to our biases. At the first start, we usually provide those weights and biases in a kind of random manner. And we get the value. Let's say we're just trying to say yes or no. And we need to collect the results and compare to what we were expecting to see, actually. Because it's a class of supervised learning. So we know when we train the data, we know what the result should be. And we need to compare it. And if there is a massive difference, then we need to propagate that error. How big is the difference? We need to start updating the weights and bias. And this is how it's done through the backpropagation algorithms. And there's a lot of math behind it. There's partial derivatives and so on. So if you want to know a bit more on the math, there's a lot of sources. So just one of them here, but there's lots of sources on that. But the idea is that you will return, so each of the units will kind of contribute towards that error. So what we're doing with calculating back, what are the errors for each of the units, and we're going back. And then there's another learning cycle, another learning cycle. There's a number of learning cycles happens so that we actually are reducing our error to the metric which we might choose is important for our network. And there's lots of them, one of them might be accuracy, another one might be precision, recall. So there are quite a few of those. So oftentimes we'll look today is accuracy. So we want to predict as accurate as possible, and this is where we're going to calculate those errors. So this is a little bit of a concept and important blocks on the deep learning. From the network architectures, there are different types of architectures available right now. And again, this is a very new field, if you like, in the industry. So deep learning, especially in the image classification, the breakthroughs happened in about 2012. So obviously big companies like Microsoft, Google, others, they've been doing a lot of research on that, and there's a lot of support there. But it's still kind of a new area, new field. So there's a lot of art to building those architectures versus what is the best approach to doing that. So there are some guidelines and best practices, but it's all moving field. So in the architectures types, there are densely connected neural networks, which is where you have all your units in all your layers connected to each other, and the data and the learning goes between the layers back, and then error propagates back. So this we'll see in a couple of slides. We'll see the example. There are special type of neural networks called convolutional neural networks, and they are used mostly for problems where there's somewhat spatial relationship exists. So vision is one of such problems, because if you look at the image, there's always those patterns, and there's always those spatial kind of relatedness between different areas of the image, of the input. And then there's another class of neural networks which are called recurrent neural networks. This is where the time and kind of space is being explored. So it might be time series analysis when there's a time is a very important feature there. It could be language and speech, because kind of when we speak, there's a specific pattern and there's a specific space. So you can't just use random words in a sentence. So there are different types of architectures available. As I said, it's still a moving field. So there are a lot of things how you could do it, as a practitioner, how you can start approaching it. There are a number of frameworks available, and I made myself a note at a bad JavaScript joke, because it's still evolving. There's lots of things. There's certain preferences. So Google's TensorFlow is obviously quite popular with the field. They were one of the first in the market. There's also others available from Facebook, from Microsoft, and so on. For the demo purposes, I will be using this library called Keras. And this is essentially a higher-level API library which can use TensorFlow at the back end. It could use CNTK or Theano or quite a few others underneath. And the reason I'm using it is probably slightly easier to read as a developer. You can just understand how the models are being built, rather than we go into details if we build it from scratch in TensorFlow. So this is what we're going to be doing. So like I mentioned, there's one of the types of neural networks is densely connected. So just want to show you an example how this kind of network's built and the parameters I mentioned to you, the numbers and calculations required. And all the units in the networks are fully connected. And there's a kind of concept where you have a number of parameters, and essentially it's each of the units. And this is what the capacity of the model to remember. So what I want to show you here is an example. And let's see if you can see that. OK. So imagine we would have a number of images which is of the specific weight. Can you see it at the back? Sorry. Is it OK? Yeah. So we have an image with rows with a height and width of 220 to 24 pixels, and it's not a grayscale. It's a full scale, full colored image. So 3 channels. And what we might be trying to predict is a 3-class classification. So maybe it's, I don't know if it's images, or the cat, dog, or bird, for instance, or something like that. And we will be, what I'm going to show you here, just an example, is how do you build the kind of network to derive such models. And you will have 1 input layer and 2 hidden layers and 1 output layer with 3 classes, and kind of bringing together all of those elements I mentioned. And so again, using Keras library, and what we do is we're building a sequential model, and sequential means that you have layer after layer after layer, and the kind of layers we use is dense. So this is fully connected ones, so all of the units will be fully connected. And then what we're doing is we're describing how our model will look like, so that kind of the skeleton of the model. So we say, well, can you create a first layer would be our dense layer, with which will take an input of the particular size we provided above. We will use our activation function relu to decide if that unit should provide data further or not. And it will produce an output space of 128 units. So the next layer will have only 128 units. So it will have 128 units of that layer. And then we'll say, OK, just create another dense layer. It will be reduced to 64, again, activation relu. And we just propagating the data in, and going so on and so on, until we get to the last layer. Our output will say, well, given the number of classes, use which of the probabilities, basically, softmax function, to decide which of the images belongs to which of the class. And if you look at the summary of the model, you can see here that we have kind of a description of each of the layers, and what's the shape, and how many parameters, or essentially how many units you have in that layer. So you can see that there is 19 million units used. And again, each unit, remember that summation function, the activation function, all of that computation needs to happen. And then it kind of reduces to the end until we have those 3 output classes. And essentially, the way it's calculated here, I just kind of explained. So you have 224 into 224 into 3, because I have 3 channels. And we have 128 neurons in this layer, and then we have 128 bias values. So it's a lot of parameters to calculate. But this is what our model capacity is, essentially. And if we look at an example, and some of you who attended other deep learning talks might have been looking at this already. So this is a hello world of deep learning, generally on the image classification. So this is our MNIST classification. So any tutorial you look at, that's where it starts. A large database of handwritten digits, then a grayscale, which is helpful for us. It's a slightly less computation required. 60,000 of training and testing images, basically different ways of drawing the numbers. And how you could build that network, now that we're a bit more familiar with parts of how you build those kind of models. So what we're going to do, we're going to, again, use the sequential models. And each of them would be dense. And we are using, so Keras, the great thing about it, if you're going to use it and try to learn some of those concepts, it comes with some of the pre-trained available data sets for you to start with. So this is what we're using, MNIST. And this is the function we're using to optimize our model, so when we're doing calculations. And so this is where we start. So we start loading and processing data. So we don't need to do any additional processing here. We just we're just reshaping it into the input for the neural network. We will have 10 classes, so from 0 to 9 to classify. And what we're doing here is, well, at this point, we're just kind of saying, well, show me how many trained samples you have, how many test samples you have. And we say, well, each of our classes, our labels will need to be categories at the output. So this is what we get into. And then when we train that fully connected network, it's, again, very similar approach as you've seen before. So you have a sequential model, and we only have 2 layers here. So we're doing a very simple model. We're doing a dense layer with this input, and we have a dense layer as an output with activation. And again, you can see it's even a simple model, if you like. You still have 500,000 of parameters to train and compute on. And when we do training of the model, so before that, we just identified as well, say, well, this is the structure of the model. So now the part is we're saying, well, when you're going to compile this model, I want you to pay attention that it's going to be a categorical, so it's going to be a classification problem we're doing here. So please use the loss function, and this is where that backpropagation algorithm works when we calculate the errors. Use the categorical cross entropy. It's one of the ways to calculate it. With a specific special optimizer, it's again one of the most typical in the first one you'd use. So when we calculate those, updating those weights and bias, and then our metric is just accuracy, how accurate we predict the values. And then when we do the training, it's fitting that model with our training data and our training data to be predicted, right? So our images and what we actually know about those images, this is what they should be looking like. And then we provide, well, this is the batch size and how many images at the time we're going to use for our network, for our model, and how many times we want to rerun it. And epochs is basically, the reruns with the same data across all of the training samples. And we want to, making sure that we compile towards that optimization for the accuracy. And then you can see, so I ran it before just in case there would be some Wi-Fi issues, but essentially we've run over those 60,000 training samples. And there is a accuracy which is identified. So accuracy is obviously between 0 and 1, so it's 92% on the training samples. And then there's an important one, which we cannot see here, but we'll see later on. It's validation as a, sorry, it's at the bottom, sorry. Yeah, so 95 on the validation set. So validation set, again, when we have our data set, we have training data, we have some of the data we keep for validation, so just kind of keep it away from the model, and then we have our test data, which it never seen before, which we'll use later on. So this is how we're making sure that the model doesn't just remember everything we give it to her, but we validate it against some data it hasn't seen, so we want to generalize it. And then you can see, so this is, again, because it's actually a solved problem, it's 97% accurate on a very small network after the 5 epochs, but it just gives us the flavor of how it works. So you can see that test loss and test accuracy, so 96%. Can we visualize the scoring process? So I found a 3D visualization of actually pretty much the same process, where you can draw your own. So we essentially have our model, and then we put it at the back of the system, and we use our images, and we draw it, and we can validate what the model thinks. And here, what you see essentially, so this will be our input space. This is our first layer of the network, and this will be our second layer of the network, and this is our classification result. So you'll see that essentially how the network works. If I put, let's see how it works. So you can see when model was trained, it learned that for number 2, the particular units should be activated. That's kind of important feature. Again, that representation of 2, because it has number, the curly thing here and nothing here. And then at the next layer, there's additional higher level representation has been defined. And then the answer is, well, first guess is 2, might be 8 if I'm doing something different. I was always surprised with number 7, because in Russia, we usually draw it like this, and it kind of throws it away straight away. So it's number 3. No, it's 7, still 7. But it kind of gets a second guess. So it's, again, depending on your data set, and this is where it's important. So I guess in US, this is how they draw without that little thing. But in different countries, there would be some different data, different bias, and all of that. So you kind of think about that as well. So this is what I want to show you here quickly. Right. So with the, again, remember, we were doing just a simple dense network. So we didn't really bother about, is it an image? Is there something important about that image, that there are some areas? It's kind of just learn as it is from images. And so convolutional neural networks is a bit of a subset and how you can optimize for vision task, because again, there is a structure to input data, there is some specific spatial relationships in the data, and there might be some repeated patterns which we might learn better from. And again, the inspiration is from our own visual cortex for us and animals. And how it usually looks like, this is the typical architecture of the CNNs, as they are shortened to. So you will have, and again, input data coming in, even if it's the same MNIST data set. And then you'll have a number of different types of layers. And these are more specific for the CNNs. And one of them is called convolution layer, pooling layer. And then you have a combination of those going through the system. So you can see how many networks you might already, many layers you might have. And then at the very end here, you'll have a fully connected or dense or densely connected layer. So basically, all the data coming in, we just want to connect it and then decide what's the output should be, again, class of 0 to 9. Is it 1 to 3, or is it yes or no answer? So, and each of the layers will have, and each of the type of layers will have its own reason to be here in this network. So if you look at the convolution layers, essentially what you're trying to do here is extract those low-level or further down the line, mid-level features from the image. And you can think of, so the image would be, again, our zeros or ones, or it would be pixels, from 0 to 25. And essentially, you think of, you have different filters applied to that image. And in our case, in the top image, if you can see, there's like 10 different types of filters. So there might be filters which are looking for just for the edges. Like here, you have, it's a filter which has, so there are zeros here, there are ones here. So essentially, what we're sliding through the image, we're trying to find where those corners of the image. Then there might be a filter which is looking for specific angles and so on. So you might, and basically, while we're doing that, again, there's just the calculations at the back of it, a lot of calculations, when we are going from a bigger image to a convolved feature, so a smaller image, essentially. And each of them, you see those matrices there towards the end, will actually extract the important bits about that image. So the first layer will get all of the edges. The second layer might get some of the horizontal and vertical parts. And then you'll have those filters. Essentially, it's like a little torch. You go across the image, and you get what's important here, what's noise, what's important here. And so you'll get a number of matrices like this. And then, again, think about that you, again, learning more representations out of the image. There's a pooling layer, which is usually after the convolution. So you start, again, condensing that. You're distilling the information out of that image. And you start, there are different ways how you can do it. You can maybe maximize, average, sum. There's different approaches. But essentially, again, you go from a bigger image, bigger feature map at this point, to a smaller one. And you keep on kind of reducing the information you have. And if you think of that conceptually, if I ask you now to draw a bicycle, what you will draw is probably, a couple of wheels, saddle, and, the whole. And then that's it, right? If I give you millions of bicycle images, this is what is important about the bicycle. And think about it. So what we're learning in the process of pressing that image is essentially what is the most, the largest features in this particular sense. And this is where what happens by the back of it, so that distillation of the information from the input. And then at the end of it, you will have fully connected layer, which will then, knowing what we've learned about the image, all these representations, so how does it actually correlate to what we're trying to predict? So what is it? Is it a particular type of animal? Is it a number? Is it a particular class of a pony? So that's where that calculation at the end happens, the fully connected layer. And again, think of that back propagation when we do that learning, so we keep on passing that information, how far we were from what we were supposed to get at the end. So I hope it kind of gives you a bit of concepts and ideas of how CNNs work. And what I want to show you now is an example of how you could build your own custom classifier. And this is where I have 3 types of, I didn't do 6, I did just 3 of those, 3 types. And each of the images is 150 to 150 pixels. And we're trying to predict 3 classes out of this model. So let me show you an example. Oops, this one. Right, so yeah, so we're building this pony classifier. Again, the results will be kind of hit and miss. My data set is tiny. I have about 100 images each, so I didn't spend too much time. You will see on GitHub it's available, but feel free to expand it on that. There's lots of other strategies to improve on that baseline, but we just want to see kind of how does it work at the back. So you're now familiar. We use carriers again. We have layers and models. So what we do here, again, putting what we've just learned into practice. So we have a sequential model. And then we have a number of convolutional layers, which will be kind of intercepted with max pooling layers to get towards the end of the layers. So you'll see the first one takes our input, 150 to 150 into 3, activation relo, and then it will then followed up by max pooling layer, and then another convolution layer, another max pooling layer. So it kind of goes on and on and on until we get to the point where we say, well, OK, flatten now all the layers. So basically bring all the outputs, connect them all together. And so we're going to have next one will be our dense layer, which will be 512 units at this point. And then bring it back to 3 classes we actually want to work. Yeah?
So what sort of process do you go through to select that ordering of layers, the number of layers, and the type of layers?
So that's a little bit of a kind of art rather than science in this case. So there are examples which you can just kind of try and follow. There are examples where you build something, you look at the results when you compile and learn, and the results not so great. So then you start either bringing more layers or playing with the kind of parameters you have. So it's a bit of that trial and error. Oops, where were we? So again, you see there's a number of parameters. So just in the summary of the model. So at some point, it kind of expands to 300. So altogether, we have about 3.5 million parameters here. And again, we are looking for the accuracy of our model, and we're predicting categorical values. So that's kind of where the specific parameters are here. And then we have a number of images. So we need to do a bit of a pre-processing of the data. And what we do is, so there are different ways of how we can deal with the fact that we actually have a small data sets. And there's one of them is we can start doing some, before we do processing, we start doing, maybe we can stretch those images, we can turn them around, we can kind of play around a little bit while we're learning, because otherwise just learning on 100 images is not going to give us great results, but out of 100 we can actually create many more. So we might be flipping, mirroring, this kind of things where basically trying to squeeze as much information out of the data set we have. And this is one of the ways of dealing with that. Because networks also learn from the data you give them, so there's no magic there, and you need to make sure that you provide variant, samples should be given a lot of variance there so that it can learn from different types of data. So this is what we're doing here, really. And then we just generating those data from, generating those image samples for training and for validations. And this is where we have this train generator, which will be used for the model, and validation generator as well, based on the folder samples we've provided. So you can see I only have 3 classes, so I have about 220 images. And then in the validation set, I have about 80 images together. And here, what we do is, so again, just a bit of information. So 16, so 150 to 115 to 3 channels. What we do here is, again, we do the training of that network I've created, the model, and then we go 30 images over 10 times. And then we can see that compared to the MNIST data set, where it was fairly good accuracy results, you can see we start on the very first run, we go into accuracy just 56%, so it's fairly, it's a random image, random weights and bias was given. It's not particularly great selection probably at this point. But then we start improving on our epochs as we go along. And but again, validation accuracy is kind of going quite high, but then actually at the end it's well, it gets to quite a high number at the 10th epoch. And again, this is kind of gives you an indication that the network is actually learning quite well, but maybe it's actually memorizing it as well, because we have a small data set, so there are certain things where we need to be aware of. So I can save this model, and then what I want to do here is just to show you as an example is we can, because we collect all of the information about how we're performing while we're training and we're validating this data. So you can see as a result, and again, these notebooks will be available for you to look at if you want later on. You can see, so our loss, and that is our error, kind of, how well we're doing, essentially, the metric of that. Kind of when we do training, we are doing spot on, right? We are close to 0, we are really good. But actually, so validation error is something which is much more important for us, because this is what the model hasn't seen before. And it's kind of a little bit all over the place, right, as you can see. So ideally, it should kind of go down as well. But again, there are certain things around data sets, around maybe not enough learning epochs, not enough learning runs haven't happened, and maybe the variety of data was not great. But it's just to give you an example of how that's done and what needs to be looked at, what's important here. And then what I did is I had a number of images in my test folder. Again, you'll see it on GitHub. So I'll just create a little predict image function, which will use my model previously created. So at this point, we don't do any more training. So that training bit takes a bit of time, depending on the kind of computer source you use. Is it CPUs might struggle, GPUs might be a few minutes. But then we already have that model. So we're just using that model to get the highest probability for the class of image. And here you can see, so I put the names of the files so that I can actually figure out what was it predicting on. So you can see it's actually, it was predicting all the classes very well. That's a good start already. But then if you actually see the score, or kind of the probability score, so for some of the classes it was pretty poor, but I think it kind of, out of 3 classes, so this was the most likely one to be. With one of the examples, which is Applejack, and those of you of My Little Pony fans, they know it's a very distinct kind of pony, so it's actually very easy to separate from any others, because others kind of a purplish, pinkish, but this one is yellow. So that particular class is very visible, very easy to learn. So yeah, Applejack won in all categories, really, so quite high up. And this is how you could do that. So I just put one of those scores so you can see. So this particular image, so it created the predicted class of Applejack, and this was the probability of it. Right, so this is, again, this is an example of how you can start building those things. There's a little bit of art to building those networks. There's a bit of art of actually, what is it you have as your compute resource, because I struggled. So I used the Azure virtual machine with GPU, so I had a small size. I actually struggled with that a little bit, so I had to take a bigger one. So there's a bit of constraints as well you might have on your, when you do this compute. On the kind of couple of things to mention. I think I already spoke about this. So machine learning models, generally, they have this problem of they can memorize very well. Whether you talk about classic machine learning or deep learning, we need to make sure we have a variety of data so that this memorization doesn't happen. We need to make sure we don't just train on all the examples, but we keep some of them separately so that we can actually validate how well model generalized. So this is a very important piece. Also, when you have a small data set, as I mentioned, you might want to create more training samples for the learning model to work with, because it has to be essentially be invariable towards the fact that 6 is turned, or to some degree, because 6 can turn into 9, and then we're in a different game here. But it's kind of, you want to kind of squeeze a little bit more out of those small data sets you have. And then another thing, when, again, you have a small data set like this, is a technique called dropout. And if you remember, we spoke about this densely connected networks. You want to say, well, actually, not all of them will be connected once in a while. And you want to, while you learn, you want to kind of drop some of them out so that the network will start learning more from less resources it has. So it's kind of constraining it specifically so that they are much more robust to this general problems. So this is some of the techniques which I've used as well. There's also another way of how you can, as somebody who develops those networks, you don't want to always go from scratch. And this is back to John's question around how do you actually build those networks, where do you start, and all that. There are lots of stuff that's been done in academia, it's already shared, and there's a lot of networks which are available, and they're pre-trained on tens of thousands and millions of images. You kind of want to leverage somebody's work already, this standing on the shoulders of the giants. And there is a ways of how you could utilize it to a degree to use it on your data. And the idea is here that you're transferring that learning. So you take a neural network, and there's ImageNet is one of those data sets which is quite famous, when I have like tens and thousands of categories there of normal images. And then you also have your own data, so you want to kind of match them together, and there's a way to do it. And it's really cool, because the idea is, if you look at the left-hand side, so you have so instead of looking left to right, we're kind of looking at from bottom to top. If we take one of those architectures, it could be a VGG16, it could be some others, Inception. So somebody, say Google, Microsoft, whoever, they already trained those architectures. There might be 150 layers there. They did all the fancy, important things, kind of tune it very well to that, to predict those types of categories. What we want to do, we say, well, actually, we want to take the most of it, because we want to use the knowledge of what is important in the images, what is kind of this high-level features. Again, if you remember those representations and kind of distillation of information. So at this point, there's a lot of information is already acquired where, which can be used later on for classification. So what we could do, and this is where there will be some of the examples, if you look at transfer learning, we will just replace the top layer, and then we will replace it with our own classification layer that could be used for our own data, for our custom data. And this is really cool, because you're kind of already using a lot of knowledge which has been done in the field, in the industry, for that. So in Keras, it's actually, again, just for your knowledge, so you can kind of say, well, use that particular convolutional base. It could be one of those models, there are many of them, and say, actually, the parameters include the top layer or not. And they say, well, don't include the top layer. Start my model, sequential model, start from this particular base, and then bring your own custom stuff. And this is where you can start building those cool things. Also, for some of them who want to go further, you can actually, not just the last layer, you can actually start tuning previous layer, and kind of go back to the start, really. But you start kind of playing with what's important here. And I'm kind of conscious of time. I have 10 more minutes. So I'll skip the demo, but you'll have it on GitHub. Essentially, what I did is I used one of those models, I think VGG16, and I said, well, these are my personal images, and actually, can you just go and use it for classification? So just an example there, and you can see the same Tower Bridge is kind of like, well, this is suspension bridge, 97% happy. So you can actually start doing that. And then at the top of it, you can say, well, maybe I want to do some other classes. That last layer, I can start training it on that. For some of the people in the room, it's all cool stuff, but you say, well, you know what, I'm a developer. I will probably, this will be my hobby, my spare time project, but actually I will never really do this thing myself. So what can I do? Can I actually expand my applications currently to do something similar, but I don't want to spend too much time. So I want to show you, just for your knowledge, one of the vision services which Microsoft provides to build, again, those custom data, custom classifiers on your own data, where you can take those models and you can create it as an intelligent edge, as we like to say it. But you can bring it onto your Android or iOS device as a separate model, which doesn't need internet. You can just go and classify whatever might be, ponies, lunch boxes, making sure you bring the right one to your daughter, because otherwise, if it's a wrong pony, that's it, right? There will be war. And these kind of things. And so this is just an example of what I did in the emulator. And how you could do that, and I don't know if you've seen that service specifically. It's called customvision.ai. It's a little bit tiny here, but customvision.ai. And so I did a very similar thing. So I've created a project. And I've added 3 classes. I've added all my images I had before. The training took definitely less time, because it takes just a few minutes to just run through that. When you do the training, I think right now it will say, well, there's nothing changed so far. But my performance of my model, first iteration, amazing. Because it's, my data, again, is fairly, it's a small data set, but it's fairly good for the models to recognize. And behind the scenes, there are transfer learning techniques being used in different ways. Essentially, of all my images, it can precisely recognize, well, with a good percentage here. And you can, as a developer, what you could do is say, well, use it as a prediction API. And you can say, well, this is my API, this is my keys, and you can either send the URL, or you can actually send the whole file and do processing of that, and you will get the results. And there's just an example is here. You can do it also in this directly here. So you can see I was playing around, especially last night, which was fun, because my daughter was actually enjoying, saying, let's do another pony, let's do another pony. So this is one of her toys. So you can see, so based on that prediction, so this particular little pony is actually class Applejack, which is pretty much spot on. However, I also noticed that this one was completely misclassified. So it said, again, Applejack, because maybe it was learned some colors or something. But second prediction is actually the one which should have been here. So again, talking about samples, the data set, which kind of should have different variety of variants here. So with that, I guess a few takeaways. So if you're just interested in using this stuff, applying it to your projects, maybe, so please take a look at this custom vision service. It's kind of nice way to start and showcase the capabilities on the image classification. If you want to build your own classifiers, have a good data set. We talk about data a lot. Lots of sample variants. Use Keras. There are lots of other frameworks. Again, choose whichever feels easier for you. I think Keras is a good starting point. You will probably need access to GPUs to make all these computations and calculations. And with the convolutional neural networks, again, start with maybe naive approach, as simple from scratch, see how it performs, and then maybe use pre-trained and transfer learning models if you want. And apply some of those techniques. And if you want to learn a bit more on kind of from a books and website perspective, so there are a couple of books which are really good. So the first one is from Andrew Truss, so he's, I think, in Oxford right now, and it goes around concepts. It doesn't go too much into math. It's a really good one to kind of understand things behind the scenes. Deep Learning with Python is written by the creator of Keras, so he explains very well how it's done, but also gives a lot of information around deep learning in general. And this fast.ai is a website where there's a lot of courses on machine learning and deep learning specifically, and I really like the little logo. Make neural nets uncool again. So make it normal, mainstream thing, which is still an issue. And for me, you may be asking what's next. Obviously, my daughter is growing, so I don't know, one of those. Still more work to do. Well, thank you very much for your attention. I really appreciate it. It's the last session of the day, and if you need any details, please look here. Thank you. And I hope I see some of you at the PopConf later on, too. Yeah. Yay.